I've said it before, and I'll say it again. Diffraction has been one of our most useful tools for understanding what various molecular structures look like. And without X-ray diffraction, it's likely that chemistry would be pretty far behind where it is right now. We wouldn't necessarily know how, atoms arrange themselves into molecules, and molecules then arrange themselves into various patterns in certain kind of materials, like crystals, especially, and like certain anytime you have repeating regular sequences in some kind of material, like a crystal, or like DNA. So let's first ask the question, why X-rays? I've been saying, we've been talking about visible light this entire time and how visible light bends and et cetera. Why would we use X-ray diffraction to probe molecules to see what the structure of certain molecules might be? Well, there is a very good reason for that, and we're going to prove it right now. So if you go to this X-ray diffraction slide, I'll read it. Nature also creates diffraction gratings. They do it naturally. Although these gratings do not look like the array of closely spaced slits. Instead, nature's gratings are regularly spaced atoms that exist in crystalline solids. For example, the figure shows the structure of a crystal of NaCl, sodium chloride, salt. Typically, the atoms in a crystalline solid are separated by distances of about 1 × 10 to the minus 10 meters. That's called an angstrom. So we might expect a crystalline array of atoms to act like a grating with roughly that slit spacing for electromagnetic waves of the appropriate wavelength. If you assume that sine of theta is about 0.5, okay, so we're taking it like it's just an average value, and that m equals 1, right? We don't really care about the higher order fringes. We're worried about the single order fringes because you don't need too many fringes to get information about an object. What wavelength of light would be appropriate for salt diffraction grating? Okay, well, what's our relationship for diffraction grating maximas? We know it very well at this point. It's d sine theta equals m lambda. Okay, the problem tells us that the spacing between these atoms is about an angstrom. So we can go ahead and say 10 to the minus 10 meters. It says we're taking kind of an average value of sine theta. Remember, sine theta goes between 0 and 1, so let's just pick 0.5. And this is m equals 1, and we want to find out what wavelength of light, of electromagnetic radiation, would that correspond to. And of course, we see that we would get a value of about 5 times 10 to the minus 11 meters. And it turns out that if you look up where this falls in the electromagnetic spectrum, it falls squarely in the X-ray spectrum. Okay? So visible light would not be able to probe distances of around 10 to the minus 10 angstroms. It's too big. It can't resolve itself in that. In fact, there'd be just mostly reflection that would happen. All right? But something that's much smaller, like 5 times 10 to the minus 11 meters, can actually diffract, maneuver itself, and create diffraction patterns through the crystalline spacing between atoms in crystalline substances. Okay? And while DNA is not a crystal, it shares a common property of crystals, which is that it repeats itself. Right? It's something that's consistent, and no matter where we shine light on it, we're going to get the same kind of pattern. And you may know, you definitely know if you've taken bio, and I'm guessing you've all taken bio, that this structure is this double helix, right? You have these two strands kind of rotating around each other, right? Again, not my best work, but you get the idea. So you get these two strands of connected base pairs that are winding and wrapping around each other. And you can see on the slide that says two famous X-ray diffraction patterns. The one on the left is crystalline sodium chloride. Okay, so that's the pattern that you get when you basically shoot X-rays through salt. All right, and then when you shoot X-rays through DNA, you get the pattern that's on the right. All right, and I share this picture not because I expect you to be able to be like, oh yeah, double helix DNA, obviously, can't you see it, right? I share this because it kind of illuminates the complexity of being a scientist, even when you know what you're looking for, right? These scientists knew, well, Rosalind Franklin specifically, knew that she was trying to find a diffraction pattern in order to illuminate the structure of DNA, how DNA was actually made, right? And she then had to look at these X-ray diffraction pictures and use the mathematics that we've done here to say, the only way this works is if you have two separate strands of molecules kind of wrapping around each other in a double helix form. And there's many more places where you can look into this more deeply as to how it was that she turned this diffraction pattern into that double helix pattern. But the bottom line is it took a tremendous amount of ingenuity and creativity and genius and mathematical ability. And, Rosalind Franklin, she was a bright lady. So with that being said, I am going to conclude this week's lectures, and I hope you just have an appreciation of this new way that electromagnetic radiation can help us understand the world.